Hello, we're going to be going over Physics Chapter 2, Homework Number 1 Solution. So this covers review question number 1 and practice problems 1 through 5 on page 69 and 70. Okay, so let's look at review question number 1. And that one says, what two conditions must be met before you can use the three equations we derived in this module? All right, well, this is on page 1 of your notes. You have to have motion in a straight line. Okay, so that's either side to side. It's a terrible arrow. Or up or down. It could be at an angle as well. All right, but then you would have to do some trigonometry. So the way we're going to do that in this chapter is side to side and up and down. So that's one thing. And then the second thing would be constant acceleration. So no speeding up or slowing down. Well, that's not the right way to put that. I'm sorry. It can't be herky-jerky type movement. Okay, so acceleration is speeding up and slowing down, but it can't be in fits and starts. All right, so the constant acceleration, you can't change acceleration during the motion. All right, so sorry about that confusion, but all right, practice problem. Number 1. So we're going to be using these three equations. Kind of smudged it there. All right, number 1 on page 70. So number 1 says an athlete runs at a constant velocity of 3 meters a second. How far will the athlete travel in 25 minutes? So I hope you notice there that we have to make a conversion. All right, so time, let's change 25 minutes into seconds. Put minutes on the bottom. One goes by the bigger one. There's 60 seconds in a minute. All right, so that's going to be let's see. 1,500 seconds. Okay, so we have time. We want to know how far. Okay, so delta x is what we want to know. It's a constant velocity. So if it's a constant velocity, what is acceleration? Acceleration is 0. All right, so we know time. We're trying to get delta x. We know that our initial velocity is 3 meters per second. So we can use equation 3. Delta x is equal to 3 meters a second times 1,500 seconds. And the second part of the equation, that 1/2 at squared, that all just goes to 0. So that's going to be 4,500 meters. All right, since acceleration is 0, the whole second half of the equation is 0. So that makes that problem number 1 to be kind of a nice, easy one. All right, let's do number 2. Promise to wash the board before the next video. All right, number 2. It says a BMW 535i can accelerate from 0 to 60 miles an hour in 7.9 seconds. What is its acceleration? All right, well, we have to decide what we're going to convert here because we have seconds and hours. Probably the easiest conversion is to take that 7.9 seconds and convert that to hours. So hours on top, seconds on bottom, 1 and 3,600 seconds in an hour. All right, your fancy calculator tells you that's 0.0022 hours. Okay, so we are trying to find acceleration. So acceleration is equal to question mark. We know that time is 0.0022 hours. We have the final velocity, 60 miles per hour. And the initial velocity is 0, starts from rest. So that would be equation 1, which I have smudged up here. So we would have 60 miles per hour is equal to 0, the initial velocity, plus acceleration times 0.0022 hours. So acceleration is 60. And you pull that 0.0022 underneath. All right, and when you do that, you get 27,342 miles per hour squared. All right. So we're going to keep that number handy because we're going to use that in number 3, that 27,000 number. Okay, practice problem number 3. It says, how far does the BMW travel during the acceleration described in problem number 2? All right, well, we know acceleration, that's 27,342. We know that time in the previous problem is 0.0022 hours. We know that the initial velocity, it started from rest, is 0. So how far we're trying to get displacement. And I would use equation number 3. So delta x is equal to the initial velocity, 0, times time, which we could just put 0 in for this whole thing, right? Plus 1/2 times 27,342 times, sorry I ran out of room here, it's not very good placement, 0.0022 hours squared. All right, 1/2 times 27,342 times 0.0022 squared. Don't forget to square that. And that will give you 0.066 miles. All right, and the question doesn't say what unit to use, so that would be fine, 0.066 miles. All right, let's do number 4. Number 4, we have a car. So a car traveling at 25 meters a second stops in 0.103 kilometers. What is the deceleration provided by the brakes? Well, deceleration is the same as acceleration. It's just going to end up being negative because we're slowing down. So first of all, let's get the delta x. We know we're going to have to change that 0.103 kilometers to meters. So you could probably do that in your head, but since it's the beginning of school, we'll go ahead and go through this. Want to go to meters, get rid of kilometers, bigger. The one goes by the bigger one, 1,000 meters in a kilometer. So that's 103 meters. All right, and we want to know acceleration, and we know it's the final answer should be negative. Its initial velocity is 25 meters a second, and the final velocity is 0. So it's a stop. So we have delta x, initial velocity. We don't know anything about time, so it looks to me like we're going to want to use equation number 2. So I would have 0 squared, the final velocity squared, is equal to 25 meters per second squared plus 2 times the acceleration times 103 meters delta x. All right, so this would be 0 is equal to 25 squared is 625 plus 2 times 103 would be 206 times a. So let's move this 625 to the left side. That'd make it negative 625 is equal to 206a. I'm just going to dispense with the units for just a minute. So acceleration, negative 625 divided by 206. So that's going to be meters squared per second squared over 206 meters. Right? And that's going to be negative 3.03 meters per second squared. All right, awesome. So we got to use the middle equation on that one. I don't think we've used that one yet in the homework. And let's finish this thing up. Okay, last one, number 5. So that one says, a rocket ship blasts off from rest, accelerates for 2,000 yards at 97,000 feet per second squared. So I'm just kind of converting that scientific notation into standard numerals in my head. You don't have to do that. What's the rocket's velocity when it's finished accelerating? Okay, let's write what we know. So delta x is equal to 2,000 yards, but we need to change that into feet, and there's 3 feet in a yard, so that's going to be 6,000 feet. All right. Our acceleration is 97,000. Again, you can use scientific notation if you want. Feet per second squared. And we know that the initial velocity starts from rest is 0. And what is the rocket's velocity when it's finished accelerating? So we want to know final velocity. Okay, so no time is involved here. So let's use equation number 2. Final velocity squared is equal to initial velocity, 0 squared, plus 2 times 97,000 times delta x, 6,000 feet. All right, that's going to be a big number. So v squared is 1.164 times, that is hard for me to, it's hard for me to read. I'm going to go ahead and put this in my calculator. All right, 2 times 97,000 times 6,000. All right, 1.164 times 10 to the 1, 2, 3. That's just 1 million. Let's see. 100, holy moly, that's a big number. I think I do want to do that in scientific notation. All right, I think that is 1.164 times 10 to the 9th. Right, 10 to the 9th. Okay, so that, if you take the square root, so let's raise that number to the 0.5 power, 34,117.4 feet per second. So, hey, it's a rocket. It's moving pretty good. In scientific notation, that would be 3.41 times 10 to the 4th. If you prefer to leave it like that, and that is perfectly fine. So that does it for the solutions to Chapter 2, homework number 1. And I will talk to you next video.